Assalamu alaikum, everybody. Today we shall be looking at multi-way trees. If you recall, we skipped multi-way trees to discuss about graphs because graphs have practical components and we needed to do the labs about graphs, whereas multi-way trees do not have lab. It's mainly theoretical. So we're going to study it in this lecture. Okay, so here is the list of topics that we are going to discuss in the lecture. First, motivation. Why do we want to learn about multi-way trees? And why is it used generally? Okay, then we explain what it is, what is actually multi-way tree. And we then concentrate on a special type of multi-way tree called B tree. B tree is the one we are really targeting at, is the one we will spend most of the lecture on. So we explain what is a B tree, and then how do you do insertion and deletion on B trees. Okay. The final topic is about a related tree, also multi-way tree, which is called B star tree. Okay, this one will be discussed very briefly. Our main concentration really is on B trees. The first thing to note is that the basic unit of I/O operations is a block, or what is called a cluster. Now here, when we are talking about I/O operations, it means reading or writing to secondary storage, like hard disk. So the basic unit of operation in that case is called a block. When we say basic unit, it means when data is read from the disk, the whole block has to be read. The whole block containing the data must be read into memory. And similarly, when writing a data, the whole block is written onto. So the data cannot be written on something less than a block. And similarly, cannot be read from something less than a block. So what does this block means, or cluster? To explain that, let us see the picture of a hard disk. You may have learned from your basic computer science course that actually a hard disk consists of flat surfaces, magnetic surface that is, which has a reader. So there could be actually more than one reader for each surface. Okay, so this thing is called a reader. It is the one that actually reads on the disk. However, to be able to read properly from the disk itself is formatted into what are called tracks. So this one in yellow is a track. So basically a small cycle around the disk containing the data is called a track. Now the track itself is divided into small parts. Okay, so each of these small part is called a sector. Now what you are seeing here in blue is an example of a sector. Now a block is actually a collection of sectors. Okay, usually multiple sectors will form a block. So what you are seeing here in red, for example, is what is called a block or a cluster. Okay, so a cluster is a multiple collection of sectors that will make a cluster or a block. So what we have just said here is the minimum data that you can read is data that is inside one block like this. Similarly, when you write data, the data must be written entirely on at least one block. Okay. To show you the implication of this, I have created a file called test.txt, and I put only a single character inside that file and save it. But see the size of that file. See, test.txt is actually 1 kilobyte. Just containing one character, but it is saved as 1 kilobyte. Now, to show you the relationship with other files that you are familiar with, I have displayed here the files we just dealt with in the last session about graphs. For example, all the graph data files containing the information about the graphs that we dealt with, they are equally also only 1 kilobyte. You see, graph data A with 9 vertices and many edges, the whole of that file is also 1 kilobyte. What does that tell you? It is telling you that in my file system, for example, the block is actually 1 kilobyte. So all this data, even though they are all these files, even though they are all less than 1 kilobyte, the minimum storage that they can be saved on is 1 kilobyte. Just like the single character file test.txt is also 1 kilobyte. Okay, graph as list class, as long as it occupies 8 kilobyte. Okay, and so on. So this shows what is meant by the basic unit of storage on a disk is a block. Okay, we're going to see what does that mean in terms of multi-way trees. Now, the other information we need to know is that reading from disk is actually very, very expensive in terms of time. Reading data from the disk is very expensive in terms of time. Each time data is requested from a disk, that is to read from it or to write from the disk to the disk, at least 3 tasks are involved. These are: 1, seek, okay, or what is called seek time. Seek means mechanically moving the disk head to position it at the correct track containing your data. So if I may just show you with the diagram here, this is your read head. So suppose your data is on this track, then moving the head vertically to reach that track is what is called seek time. So you can imagine the data that is in an inner track will take a little more time for the head to reach there. Okay, so in this track, moving the head to reach that is called seek time. Okay, the other operation that is required is called rotation. So rotation means positioning the head, that is the read head, above the correct block, okay, that contains the data. The correct block on the track. So we have reached the track, but the track has many blocks. We still need to rotate the disk so that the correct block which we are going to write to or read from will be near the position of the head. Okay, so again, just to show you from the example here, so suppose the block we are trying to read from is here. Okay, so the head is already, let's say, on that track. Now spinning the disk so that, because of course the head cannot move, it is the disk that spins. Actually, the disk constantly spins around underneath the read heads. So spinning the disk to reach the beginning of the, for the head to be just at the beginning of the block, okay, is called rotation time. Sometimes it is called latency time. All right, so this also takes time. So first we seek to locate the track, then we rotate to reach the block. Now, obviously, the rotation time depends on where the data is relative to, or where the block is relative to the position of the head. For example, if the block is here, then it will take very little time for it to reach the head. If it is somewhere here, it will take about half cycle to reach the block. To reach the head. Now, what if it is just after the head? Then for it to reach the head, actually almost a full cycle is required. Therefore, the latency time actually depends on the position of the block relative to the position of the head. So what we do therefore is we say on the average, we need at least half cycle. Okay, half the time needed for the disk to make one cycle. That is the rotation time. Okay, it could be almost a full cycle. It could be very little, just a small distance, like from here to here is not up to half. Okay, so on the average, we say half the time needed to make a cycle. This is what we are saying here. Now, on the average, this takes half the time needed to make one revolution or one cycle. Okay, so we have located the track, we have located the actual block containing the data, but we still need to read the data. So we have the last component, which is called transfer time. Transfer time is the actual time it takes the disk to be rotated so that the entire block passes underneath the head. Okay, the disk has to be rotated so that the entire block passes underneath the head in order to actually read the data or to write the data. Alright, so again, going back to our disk, the read head is already at the beginning of the block here. Okay, so but the transfer data, the transferring of data has not yet started. Now, to actually read the data, the remaining block, the entire block has to pass underneath the head. Okay, so the time needed to actually do the transfer, which means this block going underneath the head and the head actually reading the data, is called the transfer time. Okay, so all these three components, if you add them together, you have what we call access time, the time needed to access the data, either to read the data off the disk or to write the data to the disk. Okay, so it involves seek time plus rotation time plus transfer time. Let's take an example of what this actually means in terms of a real disk. Okay, so here is an example where it says, suppose we wish to transfer 5 kilobytes of data from a disk, and the disk has the following properties. 1, it requires 40 milliseconds to locate the track. So the seek time for our disk is 40 milliseconds. The disk makes 3,000 revolutions per minute. So this is the property of our disk. Some disks actually spin faster than others. So this particular disk we are talking about, it makes 3,000 cycles in 1 minute. It also has a transfer rate of 1,000 kilobytes per second. The question is, what is the access time that is needed to transfer this 5 kilobytes? Okay, so let's try to calculate it. Obviously, the seek time is given directly. Seek time is 40 milliseconds. So there's nothing to do about that. But we are not given the rotation time directly. Instead, we are told the disk takes 3000 revolutions per minute. Now, since the seek time is in milliseconds, we have to try and see how much it takes to make one revolution in terms of milliseconds. And then remember what we said, we need half the time needed for one cycle to actually be the rotation time. Now, so 3000 revolution takes 1 minute for our disk as given here. But we know 1 minute is 60 seconds. But we are not also interested in only second, we want millisecond. So to convert to millisecond, we have to multiply by 1000. Okay, so 3000 revolution takes 60,000 milliseconds, if you like. The question is, what will one revolution take? One revolution or one cycle will take this amount divided by 3000, which is 20 milliseconds. You can see that the 1000 will cancel the zeros here, and we just have 60 divided by 3, which is going to be 20 milliseconds. So if our disk makes one revolution in 20 milliseconds, what will be the rotation time? It will be half of this. Therefore, the rotation time for our disk is half of 20 milliseconds, which is 10 milliseconds. Now, the last component, we are told our disk has a transfer rate of 1000 kilobytes per second. So again, since we have converted the other times in milliseconds, we should also try to convert this to per milliseconds. Okay, so the transfer rate is 1000 kilobytes per second, but 1 second is actually 1000 milliseconds. So the transfer rate is 1000 kilobytes divided by 1000 milliseconds, and therefore it's actually 1 kilobyte per millisecond. In other words, 1 kilobyte is transferred in 1 millisecond. But we have 5 kilobyte transfer. Therefore, the transfer rate for our 5 kilobyte will be 5 milliseconds. Now, if you add all of this, we will have 40 plus 10 plus 5, which is 55 milliseconds. So it will require 55 milliseconds for our disk to actually transfer 5 KB. That transfer could be either way. It could be reading from the disk or writing to the disk. All right. Now, what does this show? This example actually indicates that transferring information to the disk is in the order of milliseconds. On the other hand, the CPU on most modern computers processes data much faster than that. For example, it could be in the order of microseconds. Now this is 1000 times faster than milliseconds. In fact, some modern computers now can process information in the order of nanoseconds, which is 1 million times faster. So now just imagine the processor is processing data at this rate, but at some point it has to wait to read data from the disk. That will make the whole program to slow down, especially if it has to read the data many times over from the disk. Okay, therefore, for a program that constantly uses data that is stored in secondary storage, when you are writing your program, especially when you are creating the data structure to store the data for your program, you have to take into account this slow access time of reading data from secondary storage. Let's take an example of binary search. So for example, a binary search tree which has many nodes can be spread over many different blocks on a disk. Okay, so here for example you have 3 nodes in one block, another 1 node in another block, and so on. So the data is spread across several blocks, and we know that reading data cannot be done in we cannot read more than one block at a time. So this tree has to be read 1, 2, 3, 4, 5, 6, 7, 8 times in order to read the entire data. And this is the problem that we are trying to solve. Okay, if the data is in the RAM, no problem. The binary search tree is very efficient. Okay, but if the data is in the secondary storage, like a disk, then definitely binary search tree, which was very efficient if the data is in the RAM, now becomes very inefficient. Okay, so that's what we are saying in this 2 point, that inserting and deleting keys in this tree require many disk accesses because each block has to be accessed separately. So the BST, which is such an efficient tool when the data resides entirely in the RAM, turn out to be inefficient in this case because we have to read the data several times, and each time we go and read, it takes much more time than the CPU is processing the data. So that's why we need another way to represent data that will minimize this number of disk accesses. To buttress this point, let's take another example. Suppose instead of 5 kilobytes, we wish to read 10 kilobytes from our disk, the same disk that we discussed in example 1 with the same characteristics. Now, let us consider 2 scenarios. In one scenario, let's say the entire 10 kilobytes is saved in one block of memory. Then in that case, the access time is very similar to what we computed before. The seek time is the same. Also, the rotation time is the same since the data is in one block. Just locate that block. The only difference is in the transfer time. It will now take 10 milliseconds instead of 5 milliseconds. And therefore, the total time that you will need to access this data is 60 milliseconds. This is scenario number 1. Scenario number 2 is suppose that the data, the 10 kilobyte data, is split into 2 different blocks. Okay, so however, if they are in 2 different blocks, then the access time is going to be twice what we computed earlier, because there will be a separate seek for each of the block, there will be a separate rotation for each of the block, and there will be a separate transfer for each of the 2 blocks. So you just need to multiply what we computed earlier in example 1 by 2, and you can see the difference. We're going to need 110 milliseconds. This is nearly twice as much as what we need in the first scenario here. 60 milliseconds against 110 milliseconds. So it is therefore better, based on this example, to access large amount of data at one time. In other words, be able to save as much data as you can in one block and be able to read it one time or write it one time, rather than jump from one position on the disk to another to read your data. Okay? In other words, the bottom line is Disk accesses is very costly. If possible, the data should be organized to minimize the number of disk accesses. And this is exactly what multiway trees are going to do for us. Instead of saving small chunks of data in different blocks, multiway tree is trying to pack as much data as possible in one block, so that we reduce the number of disk accesses and therefore make our programs more efficient. This is basically the motivation why we want to learn about multiway trees. They are generally needed when the data is so huge that it cannot be saved in the RAM. Okay, usually, for example, database systems, the data cannot all be in the RAM. The data is in the secondary storage. So most database systems, they actually use a kind of multiway tree to manage the data, so that the data, the disk accesses will be reduced. Okay, so let's define what is multiway tree then. A multiway search tree of order M, or sometimes called M-way search tree. Notice that it is a search tree, like BST and AVL. We will see that in a moment. Okay, so a multiway search tree of order M is a multiway tree in which we have the following. 1. Each node has at most M children and M-1 keys. So actually it is just an extension of binary tree. In binary tree, the keyword there is binary, which means 2. So the M in case of binary tree is actually 2. In binary tree, we have each node will have 2 subtrees, 1, 2, and we call them left and right. However, here in multiway tree, we extend the number to M. So these subtrees 1, 2, 3, and so on, there will be M of them. Okay, from 0 to M-1 means M. Okay, so each node has at most M subtrees, not 2 subtrees like binary, but M of them. And therefore, M-1 keys. Like binary has 1 node in each key, which is 2 minus 1. So similarly here, the keys are going to be M-1. If you count them from K1, K2, K3 until Km-1. Okay, so this is one property. 2, the keys in each node are in ascending order. So K1 is less than K2, is less than K3, and so on, and less than Kn. Alright. 3, the keys in the first I children are smaller than the I's key. So let's say our I is 2. So we are saying the keys in these 2 subtrees. Okay, subtree number T0 and T1, there are 2 of them, will be less than this key 2. So basically what we are saying, all the children on the left of a key, the data in all the children are to the left of our key K2 will be less than the value inside K2 itself. And the keys in the last M-I children are larger than the I's key. So basically the children in the right side, they're going to be M-2 of them. Okay, so M-I. So all the data here will be larger than key 2. And the process is repeated for the other keys. So for example, for K1 here, the elements in T0 are going to be less than K1, and the elements in T1 and so on until the end are all larger than K1. and so on and so forth. So essentially, this is just an extension of binary search tree. This is why it is called a search tree. You can easily search. If you come in with a value, you just need to go through this key until you find where it is greater or less than. Then you take the branch and follow that tree and so on. So this is the definition of a multi-way search tree. It's just an extension of binary search tree. As we shall see later, the idea is instead of saving one key in a block of secondary memory, we save the entire node. Okay, all these keys will be saved in one block. So we read all of them at one time rather than many times. This will save time for us in terms of disk access. Okay, let's see a real example of multiway tree. So this is a multiway tree where we have the keys. I think the M here is 4. So the maximum number of subtrees, yeah, it is written here, figure 7.1, a 4-way tree. So M is 4, meaning the subtrees 1, 2, 3, 4 is at most 4. Okay, it can be less, but at most 4. And therefore the keys in the node themselves are 3. Always M minus 1. So 3. Okay. So it's not all of them that will meet this criteria. These are just the maximum. The maximum number of subtrees is 4, and therefore the maximum number of keys is 3. Okay, but we can observe the following regarding this tree. So in a multi-way tree, the leaves do not need all be at the same level. So you can see this is a leaf node, this is a leaf node, this is a leaf node, and this is a leaf node, and they are at different levels. This is actually not good. Okay, this is why we want a multi-way tree that will have all the leaves at the same level. And that's why we're going to study B trees. Okay, so this is one issue with general multi-way tree. The leaves may not all be at the same level. Second point to note, a non-leaf node with n keys may contain less than n plus 1 non-empty subtrees. Ideally, if we have 3 keys, we should have 3 plus 1 subtrees. But here we have 3 keys and only 1 subtree. Okay, 2 keys but only 1 subtree, and so on. So again, this is not ideal. What we want is if we have n keys for a node, then there should be n plus 1 subtrees. Of course, here n should be less than or equal to m, because m is the maximum you can have for a multi-way tree of order m. Okay, so therefore, what we can conclude from this observation is that, like BST, multi-way trees can be unbalanced, and therefore there is a need for a mechanism to balance it. And that is why we need to learn about the special type of multi-way tree, which is called B tree. And that's what we're going to study next. And in fact, that will be our concentration for the rest of this lecture. So what are B trees? A B tree of order M, where M is greater than 2. Notice here, if it is 2, then it is just binary. We don't want a binary tree. It has to be greater than 2. It's a multi-way search tree of order M with the following properties. Okay, 1, the root is either a leaf node or it has at least 2 non-empty subtrees. So this is one condition we are putting. In a normal multi-way tree, any node, including the root, can have only 1 subtree. But here we are saying the root must have at least 2 subtrees. Okay. Yeah, so this is one restriction we're imposing on our multiway tree. The root must have at least 2 non-empty subtrees. Second condition, a non-leaf node other than the root must have at least the ceiling of m/2 non-empty subtrees. Okay, so this is even more stricter than our condition here for the root. First of all, what does ceiling mean? If you take an m like 5 over 2 will be 2.5, right? Now the ceiling of 2.5 is the lowest integer that is greater than 2.5, which means 3. Okay, so ceiling, you go up to get the ceiling. Floor, which we don't need for this lecture, is you go down. So if you have a fraction like 2.5, then the ceiling is the next integer bigger than that fraction, so which is 3 in this, if m is 5. Okay, so if, for example, m is 7, then 7/2 is 3.5, so the ceiling will be 4. So we are saying the root is allowed to have at least 2 subtrees. But other than the root, every node that has subtrees, okay, of course, leaves, they don't have subtrees. That's why we again say non-leaf. Okay, so each non-leaf other than the root must have at least ceiling of m/2 non-empty subtrees. So if you have a B tree of order 5, like we said, each non-root node, or all the internal nodes, if you call them internal nodes, the nodes other than the root and the leaves, they must have at least 3 subtrees. If m is 7, they must have at least 4 subtrees, and so on. So this varies depending on the value of m. Only the root is allowed to have only 2 subtrees. All other non-leaf nodes will have more. They will have ceiling of m/2 subtrees. Okay. Next is that the number of keys in each non-leaf node is 1 less than the number of non-empty subtrees for that node. We saw in multiway tree that you can have 10 keys but still only 1 subtree. Now in B tree that is not allowed. In B tree the relationship between the keys and the subtrees must be the number of subtrees is equal to the number of keys plus 1. Okay, so if you have n keys, you must have n plus 1 subtrees. If you have n plus 1 subtrees, you must have n keys. Okay, that relationship must be maintained in a B tree. And the last condition is that in a B tree, all leaves must be at the same level. All leaves must be at the same level. So basically, these are the restrictions that we're going to impose on our B tree so that it remains balanced, unlike a normal, ordinary multi-way tree. This table actually summarizes this restriction that we put here. It's important to try to remember this. Simple questions can come in the exam or quiz relating these numbers. So here I try to group the relationship in terms of number of subtrees and then the number of keys. Also, we consider the nodes in the tree to be of 3 types: root, internal nodes, So all nodes except the root and the leaves, and then the leaf nodes. Okay, so and then for each of these we have maximum and minimum. Maximum and minimum. Let's concentrate on subtrees first. Okay, so obviously no node will have more than m subtree. This is why the tree is called m-way. This is the maximum. So the maximum number of subtrees, whether the node is a root or a non-root, is m. Of course, leaves don't have subtrees, that's why they are leaves. So the maximum is 0. So I think this is very obvious. The maximum number of subtrees you can have for any node is m. And in fact, for a leaf, because it doesn't have subtrees, is 0. Okay, maybe we can jump and talk about the maximum number of keys, therefore, because the keys, you just subtract 1 from the maximum subtrees to get them. So it means the maximum number of keys for a root is m minus 1, because it will have m subtrees, therefore m minus 1 keys. Similarly, for the internal nodes, since the maximum is m subtrees, the maximum number of keys will also be m minus 1. What about the leaf nodes? Well, the leaf nodes, they don't have subtrees, but they do have keys. The same rule applies. They cannot have more than m minus 1 keys. This is the maximum. All right? Good. Now, so that's the maximum. Maximum is very easy to remember. The maximum keys is m, and therefore, maximum subtrees is m, and therefore maximum keys is m minus 1. What about the minimum? The minimum is the one you need to remember. For the root, the minimum subtrees is 2. You cannot have one subtree for the root. So the minimum subtrees is 2, and therefore the minimum key is 1. You can have 1 key in the root. Maybe this is the first element you are adding, so you can have 1 key, but this is only for the root. For the internal nodes, the minimum subtrees that you can have, as we explain here, is ceiling of m over 2. So it depends on the m, therefore. If m is 5, then the minimum subtrees is 3. If it is 7, the minimum subtrees is 4, and so on. So the minimum keys will be this number minus 1. This is always the relationship between the number of subtrees and the number of keys is that the number of subtrees is 1 plus the number of keys. So if this is the minimum for subtrees, just subtract 1 to get the minimum for keys. Alright, what about the leaves? The leaves, they don't have subtrees, so the minimum is also 0. Okay, for both minimum and maximum for leaves is 0. But they can have keys, and the number of keys is the same as for internal nodes. Minimum of ceiling of m over 2 minus 1. So this is the criteria that our B tree will satisfy, and with this you will see that it's going to be balanced. So according to these conditions, a B tree is always at least half full. It has few levels and it is perfectly balanced. Okay, let's see example in the next slide. Example of a B tree. So this is an example of a B tree of order 5. Okay, so as we remember, the root can have 1 key and therefore 2 subtrees. You don't have to draw the empty cell. This is just for completeness. You can just say 50 and then you have 2 subtrees. So this is fine. The root can have 1 key, but any other node must have at least 2 keys, because ceiling of 5 over 2 is 3 and 3 minus 1 is 2. So the minimum number of keys in any other node must be 2. This is the minimum. As you can see, the remaining nodes, they all satisfy that minimum. This is 3, this is 2, so this is at the minimum actually. 2, 2, 2, and so on. But the maximum is m-1, maximum keys, that is. So this node is actually in its maximum state. It has 4 keys. It cannot have more than 4. Okay. So that's in terms of keys. In terms of subtrees, none of the node is at the maximum yet, because you can see this node has only 1, 2, 3, 4. Okay, we can have one more subtree. Okay, so none of the elements here is at the maximum in terms of subtrees. And notice the relationship. This is very important, Shabab. The number of keys must always be less than the number of subtrees by exactly 1. So if you have 3 keys in a non-leaf node, it must have 1, 2, 3, 4 subtrees. This is a common mistake that students have when we come to insertion and deletion. You will see that they have 2 keys, they have 3 keys, but less than 4 subtrees, which is not acceptable. Okay, so we will see that when we come to insertion. So this is an example of a B tree of order 5. Let's take some few more. This is a B tree of order 4. Now for order 4, the ceiling is already, the ceiling of 4 over 2, that is already an integer. And 4 over 2 is 2. So the ceiling of 2 is of course 2, because 2 is an integer. So what that means is you can have minimum of 2 subtrees for a non-leaf node. Okay, and you can have a minimum of 1 key, because 2 minus 1 is 1. So this is fine for a B tree of order 4. Okay, yeah, so this node is in maximum state, because for order 4, the maximum keys we can have is 3. So we already have the 3, and therefore the maximum subtrees is 4. 1, 2, 3, 4. Okay, this is another example, order 5 again, but this time we have a full node. This root node is full. It has 4 keys and 5 subtrees. The 5 here is for the subtrees. 1, 2, 3, 4, 5. It cannot be more than 5. Okay, so again, this example is showing that the elements that you store may be letters, maybe string, maybe any object, not necessarily numbers. So this is basically what a B tree is. The question is, what use is it for us, especially if you relate it to the motivation that we started with earlier. Okay, so here it says B trees are suitable for representing huge tables residing in secondary memory. Okay, so if you take database system containing a lot of data, for example, if you go to registrar's office, all the student records are saved in the database. So it's a huge amount of data, not only the current students, but also the past students. So obviously you cannot have all of this data in the RAM. The data is normally in the secondary storage. And things like B trees therefore are used, or data structures like B trees are used to manage the data. Okay, because as we said, with a large branching factor M, the height of a B tree is low, resulting in few disk accesses. As you saw there, in the example that we just saw, the height can be really very low compared to if we are to store the data in a BST. The height is going to be much taller. The second point is the branching factor M can be chosen such that a node corresponds to a block of secondary memory. So depending on the file system you are using, check to see what is the size of a block. In my file system that I showed you earlier, the size of a block is 1 kilobyte. So for some system, it could be much more than that. So you should define your M such that the data in one block can be, the data in one node can be saved in one block, so that you read the whole node one time and you write the whole node only one time. This is the way actually the tree will give us advantage. It will reduce the number of disk accesses. Okay, so B trees usually keep related records on the same block, and therefore when you read, you're going to read all of it in one time. So again, this results in fewer disk accesses. This is basically the advantage of this tree compared to other trees that we have seen before, like BST and AVL. Okay, this one is designed with the consideration that data is going to be saved in secondary memory like a disk, and reading data from it will take a huge amount of time relative to if the data is in the RAM. Therefore, we try to reduce that number of times that we need to go to the disk by storing as much data as possible in one block, okay, so that we read the whole data one time.